so it might be a little disjointed there. So I was doing, okay, so I'm doing radar cross-section imaging and then with super resolution, but as I got more into it, I was like, maybe I should also focus pretty heavily on radar, what RCS actually is with radar cross-section imaging. So there's a little bit of super resolution as well, but I'm kind of going to go over the whole basis of the concept and what it's used for, so you have a broad overview of the topic. So basically, you have to there's a lot of things you have to know how radar works. You got to know how what cross-section imaging is, what SAR versus ISAR, and then we'll get into super resolution theory, how that kind of all ties it together. I'll go over some of the techniques they're using in the topic I'm particularly talking about, and then I have some real-life examples of what I use it for in my work. So, what is radar? It's radar stands for radio detection and ranging. It's a method of detection. It was originally used to find planes in World War II. The Allied forces used it to help detect German planes. And the idea is that you use the Doppler effect. You shoot some rays out, some electromagnetic energy out, and then when it bounces back at about the same frequency, you can use the Doppler effect to see how far something is. And this can be used for vehicles, planes, missiles, weather formations. This is the typical use when you're trying to detect a range. Radar has since expanded to a multitude of things, from scanning to like 3D scanning, and then SAR, which I'll talk about more. And then just a basic thing is that you have a receiver and transmitter. The radar antenna will shoot rays. If it hits something that can reflect, either what's going to happen is it's either going to reflect, it's going to scatter, or it's going to be absorbed. When you have planes like stealth aircraft, they rely on either scattering it away so it doesn't come back to the antenna. They have, it's called mag-ram materials, which helps absorb the energy. And in the best case, if you're trying to detect a plane, you'll get some signals back. So this brings us to radar imaging. What can you do with, when you receive this data, what can you do with it other than just have an idea of where a plane is in the sky? So IEEE defines it as defines what an image is a spatial distribution of physical property, such as radiation, electric charge, conductivity, or reflectivity in our matter, and then you map it. So it's just like taking a picture, except instead of worrying about the optical data of that's what you're getting with a picture, you're worrying about the reflection data. And that comes with some caveats. It's a little bit different when you're trying to interpret three-dimensional data, especially with depth. So, like an interesting thing with RCS is that, and you can see kind of in this is an example of a plane in its signature. This is taken, and what this shows is that it shows you the range. If radar were to hit you, it would show you what direction it would scatter, and that's important in the defense industry because if you're an aircraft, this can tell you if that was in, say, kilometers. It'll tell you that anything that hits you at 25 kilometers is going to also see you, and you can use that to help navigate through terrain in hostile environments. That's what we use RCS images for, and the processing, I'll go over how we get that data later. But that's just what it all comes to, is generating these kind of images to help make assessments. That's a big part of using it for avoiding anti-air countermeasures. So some of the techniques involve direct scanning, which is just like if you had a camera, you have an antenna with an aperture, and you'll have some 3D object, and you scan an area. In particular, like if you had a plane stationed up, and you would scan each part, and you would take the measured data back, and you can use that to reconstruct images. And that can either be 3D images, which kind of what that, if you come back to, that's what you start getting if you take all the data and wrap it around, or you can get 2D images. That's what spot scanning is, and that's how you can get projections. That would be your equivalent of taking a picture of something. You can use radar to form a 2D image that you lose what the range is, but you get an idea of what it might look like, and that's really useful for target location or identification of whatever your target is. So, and then you have a problem though, is that you have to have a pretty large aperture to get high definition images, and that becomes expensive and also becomes really hard, and also you start having issues with, if your aircraft is huge, like a 747 or something, it becomes very difficult to actually scan it, because you have to worry about, there's things called near field effects, which basically that whenever you're actually using radar, you're only worried about it when it's far away, but when you start taking images at a close range, you get a lot of noise and data that's not really going to be there, and that becomes an issue. And that's where a lot of the computer vision techniques of having to filter out data or using other techniques like super resolution will come into play. So SAR imaging helps remove the fact that you need physically large objects. You can use small antennas, and this is a type of cross-section imaging, and I'll go over in the next slide of how it works. But basically, the idea is that it scans an image with the motion of your radar. So if you had a plane and you're flying, you take a bunch of images as you fly, and all those captured samples over time help you put together an idea of what you're looking at. It generates a synthetic aperture, so now the distance that you've traveled becomes the size of your aperture. So if you needed a huge 10-foot antenna, you can now do it with a 1-foot antenna over time, essentially. And then inverse SAR, ISAR, is just the inverse, where instead of you have the antenna moving, you have a stationary antenna and you scan an object that's moving. And they're both used for different things. Very useful for target identification is what ISAR. So the principle is that, again, you have, in this case, it's a satellite moving, and as it moves through space, you keep scanning the ground, and you can use the echoes, the Doppler effect. So what traditional radio's for is you can use that energy reflected back, and you keep taking all those images and you put it all together, and you can help generate a single image. And it creates incredibly high resolution images to traditional SAR scanning, and I'll show pictures on the next slide. So you have to use a lot of image processing, and in particular, a lot of the math in this, if you haven't taken digital image processing with Havlicek, I highly recommend it. It's and also DSP, Havlicek's other class. It goes into how you can filter out the data. There's a lot of the math gets pretty complicated. I'm not going to bore you all with that. But those classes, if you want to really get into how to deal with, because you're getting a lot of complex data and with a lot of noise, that's where you want to be. Yeah, you have to use a lot of Fourier analysis and linear algebra. So here's an example. This was taken from the Space Shuttle Endeavour. It's a volcano, and you can see there's the green represents the greenery and stuff. So they're able to get some color out of it too. But you can see just how detailed this is, and this is from the Space Shuttle. So it's pretty incredible. They just kept taking pictures and kind of put it all together, and you generate this image. So it's used a lot, especially on different planets where traditional optical imaging is not going to work, right? If you have to deal with optics, it gets blurred by the air, whereas radar can pierce through. So if you're using the right frequency, can cut right through whatever clouds or whatever gases you're dealing with, which is always a problem when you're taking pictures. And you can use all this data to generate a nice 3D image. So now I'm going to go a little bit into what super resolution. Basic concept is it's more super resolutions is just, there's a bunch of different techniques just depending on what you want to do. So traditional thing is that you can use it to remove noise. So if you have a bunch of low quality pictures, you can kind of combine them to get a higher quality image. As you can see, it's kind of hard to see in this light, but the image on the left side, we got a lot of noise in it, and then the right side really cleans it up. This is really useful for satellite imaging in particular, which can be plagued by really bad low resolution. Especially in the old days, planes did not have as great cameras as they did now, and that was a big issue dealing with that. So the basic concept is you take something of really low information, and by low information it's an object that is full of noise, or you just don't have the resolution you really want, and you basically take all those different pictures and you can put them all together to get more information out of something. And that requires a little bit of statistical analysis and using inferences. So you kind of interpolate. So like a lot of when you use like going to the frequency domain or the frequency domain, you try to ideally keep your stuff linear. But when you're using super resolution, you kind of you lose that ability to go back because you're kind of putting your own emphasis on what you're trying to guess, essentially. So this comes back to RCS signature is when, like I mentioned, when you're scanning something at a very close range, you get near field effects, which can cause a lot of noise. And super resolution is really good for helping to remove these artifacts, and you can get better predictions in the far field, basically when you're actually using the radar of what you might be looking for. And that's called speckle noise, and that happens a lot in SAR and ISAR. And basically you get really big, loud blurbs that aren't really there, but the radar thinks it is, and that can be due to a multitude of issues. And I have pictures and stuff. I'll go over that at the end. So here's some techniques. This one was just like, so the big thing with super resolution SAR imaging is that you have to capture a lot of images. Well, if you're flying over something, in particular, if you're flying over something really fast and you don't have a lot of time, you might not get as much images as you want. So say you have this landscape, you can kind of see this is some sort of city, right? And you can see a river, and you see the top section that's focused is a bridge. And what they did was, in this particular instance, they took several low quality, they took the same image, they had a few of them, but then they polarized it to kind of get different effects. Specifically, they were able to get a lot of edge artifacts out, and then they used super resolution to combine all of those different polarizations of the same image. So you kind of exponentially increase the amount of samples. In neural networks, you can do that. They do a lot of, to build your test samples, you can take an image and do a bunch of different things to it to help build your test set. That's kind of what you're doing here. And there is ongoing research of using neural networks now to do this techniques to help do identification.
When you say change polarization, they did it after the capture?
Yes, after they've captured the image. So they do like, I'm assuming they do like some kind of
then you say it has
high frequency, low frequency, high pass filters to help get edges and then kind of interpolate all that data together. I've linked the article for more details.
So it can, if it's just trying to capture the brightness or the intensity of the each pixel, I guess it doesn't have information to change the polarization as post-processing. Do you think that they are capturing something like more than that, like light field, or like do you aware that, like for example, I know like commercial-wise they have light field cameras. If you can capture also the direction of the light information, then you can do, like, for example, like post focusing.
Oh, that might have, I thought it was. I assumed when they were talking about taking like a high pass filter and using that to kind of and combining the image to kind of sharpen. I guess was what I was thinking they were doing, to help sharpen the images, and then use that with the original image to kind of get you a better idea.
Do you have a reference here? Like,
yes, yeah, I have a link at the end,
yeah.
and it's at the end of this.
Okay.
This one's more of what I'm interested in. What we do is that use Bayesian induction. It's basically a lot of radar there's a diffraction. A diffraction limit's basically like where you don't have an idea of, you're at the limit of what you can capture information wise. So the technique this is power, how much power you're putting in an object. So in the 0 dB, that's how much power you got back. So it's full of a lot of a noise that you can't really filter out of. But in the bottom is what they're using, what they're suggesting, their technique for super resolution, and that's to, even at low power, you can get a shape, and you kind of see it's some sort of plane, and they were able to basically remove all the noise, which is really important in identification. Is and usually you have fairly low power, so the idea is that other techniques traditionally were they're able to kind of remove speckles, or they're in the top case it's just the raw data, but you can remove as much noise as possible. It's not affiliated with your target, with as little information as you have, and use that to now identify what you're looking at. And this takes a lot of statistical models to help draw conclusions of the pixels around you. You basically get like a lot of radars you'll have, and a lot of techniques require like you have to do everything has to be evenly spaced. You have to do even sized image, and you kind of get like pixels in between that don't. The way the math works out is that you end up with highlights where you should have like 0 points or like localized singularities, but they might be absent because of the way you've done the processing. So you kind of use this to expand upon the image and get better resolution.
Sorry, like what's MDA?
That was another way that they were able to help remove noise. I actually don't. It was just another technique they used. The one I was focused on was on the Bayesian technique. This was proposed, and this is also linked, is a proposed thing to. This is the one we at our work is what I use. That's why I was focused more on it.
Mm-hmm.
And basically, you're using statistics now to remove noise these noise objects that are coming out of your image. And this is really good, and you'll see a lot of noise like this, especially if you're doing a near-field sampling of an image. You'll get noise effects that aren't really going to be there. So now this comes back. Now if you take this and you go into what you're actually using ISAR for, so in the military you're using ISAR to identify targets. So you have a stationary radar and it's scanning something out in space, something out and what by being in space is some region. A lot of times they take planes and they will basically build a data set with them. So you have like your perfect idea of what it's going to look like, and that's what the top pictures represent. These are different planes that they've scanned, and it's kind of hard to see, but there's you can see colorations of zones that really show up. So in particular, if you can kind of see, there's red lines at the front of the wings, because that's where most of your energy is reflecting when you're doing RCS imaging, because that's the most of your energy hits that flat surface and bounces back. And then they've taken that and kind of highlighted what the shapes of these bodies represent and what they're looking for. But real life data is not like a model. You have very little information actually go on when you're scanning something, and seconds matter with a lot of these situations. So, and it's really hard to see in this. But you can kind of, there's basically in the bottom image is a real life example of a plane flying, and you can see just a few. It's really hard to see in this lighting, but there's a few. Actually, I can switch over to the camera to show. So here's a good example of a plane, and this is kind of the highlighted information. They've taken the scan of the image, and you can see where depending on which way you're looking at. So this is from the front view. You get this good idea of how much energy you're getting back. And in particular, you can see anything that's got a big flat surface, when radar hits it, gets you the most energy back. And then you can plot that over basically the range. So you get you get kind of a projection of what everything's reflecting back. So it's very different than traditional imaging. You're not trying to get an image of what the plane looks like. You're trying to get an image of how the plane responds to radar energy hitting it. So if you have things like cavities, you can get weird smears and stuff, because what happens is things will ring around inside and it'll look like it's farther back than it is, and this requires a lot of post-processing and sometimes some kind of guessing, and almost all these systems require almost immediate responses, so it takes a lot of planning and modeling and just predictions, and hopefully you can get the right prediction out. Here's another example. So this is from the back side. You can see that since all those faces are no longer facing the way of the radar, so if the radar was coming back towards the tail end, the spikes you get when it hits those surfaces are now coming back a lot smaller. And there's other weird artifacts you get. So if this was a plane and you were shooting and you're hitting the radar, the way the surfaces are responding, you might only see energy here and here, which is problematic because that doesn't really look like a plane. You're not getting your ideal image out like you are here. You're not going to see that. Oh,
it's coming back. Yeah.
You're not going to get that top model. you're going to get really high marks. So you can train systems to say, well, we know this plane always has this distinct, it has like these 4 points, which comes back to, they have a picture of when you have missiles, they have very distinct, missiles have a very distinct thing where, you know, they don't have wings, so you're going to get reflections on the back, and then you'll get some on the front and the back end, and but no wings. So that can kind of tell you, oh, we're not dealing with a plane where a plane always has some sort of energy on the sides. You only have energy on the front face and the back end, so it's something that's got to be long and cylindrical. Or here's a training drone. You can see the differences. You have some energy here and some here, whereas a traditional missile is not going to have any side artifacts. And you can use that then to infer what you're dealing with. So then this comes to what I do is we try to do predictions for our RCS signature. So you see these spikes. A lot of, if you've ever seen an F-117, that was the old, like really weird plane that was like, had a lot of faceted faces. It was done in such a way, so it's done for that reason, so it scatters energy away, because you can't truly get rid of all the energy, but you can push it in different directions where the radar might not be looking. So the idea is that while you're flying, you say, okay, I can hopefully sneak in between whatever radar, or if I'm coming directly at it, they're not going to see me until I'm literally right on them, and then it won't matter. But you have to be very cautious that you don't let any of those, your star, which is what those spikes are, you don't want any of those star edges to hit the radar, because then they'll see where you're at. And this is, a lot of stealth technology is basically based on this. It's like 80% the shape of the plane. So the B-2 is a great example. It's shaped in such a way that almost everything is plane form aligned. And what that means is that all the energy gets reflected in specific directions, and so you know where your energy is going. And then there's 20% of using materials to help kill signal. There's other shapes, like the engine is buried inside, so you don't have to worry about a flat face, and a lot of energy just gets scattered out and pushed back or never comes back to the target. And that's a good majority of what RCS does, but there's I'm going to show some on the board basically of how you capture RCS and like why computer vision is important for interpreting that data, because it takes a little bit of work to get from scanning something to this diagram. So, if you're in the defense side, it's awful to see, but basically in the real world, you have different types of radar, one that's really long range, and it's like, okay, there is something out like 50 miles out. We don't know what it is, we just know there's something out there. And then you have to react quickly, so usually what you do is you have jets go and try and get closer to try and get a better picture, or use other radar to focus in that area to get you a better picture of what you're looking at. So you start scanning it with some sort of ISAR, and you try and identify, so you start trying to get those spikes again, trying to see what we're looking at. And this is important, and this is where a lot of computer vision comes in, is because you're running on a timer. If a plane's 50 miles away from you, you might not have very much time to figure out if you need to react or not. And hopefully you can use this data to properly identify an aircraft. And then in the offensive, you have another thing where you have a plane, and what we do is we scan the plane to help get the idea. We get that signature, and we know what it's going to look like in the far field. We know what it's going to look like if they start scanning it, and hopefully we can either remove any kind of identifying markings or perhaps manipulate it so it looks like something else. We scan that, we use it to construct those RCS diagrams, and then we can use that to now determine if wherever we're going can actually be accessed. And this is really important because you don't know if you're dealing with a plane that's like this, or if you're dealing with a plane that's like this, because how you react is going to be very different, and you want to be very certain of what you're dealing with. So I was gonna just, is there a way to turn off the, projector? I was gonna draw something on the board because it's a lot easier for me to do that.
Yeah, you can just switch to any, yeah, you may turn off the projector.
I'll just turn it off.
Or you can just turn it whiting on the other side or something.
Okay, if that will work. I didn't know if you want to go scan it.
Yeah.
Just want to move the camera.
Yeah, let me just say.
Actually, so so a lot of times when you're scanning something, your diagram kind of is based on you have some sort of target. So you have your plane in the middle, and you have a band essentially, but you're very limited. This is where you start having issues with when you're on the fringes. A lot of the math will, in particular when you have to do like zero padding, you have to do it with radar too, because you start getting weird artifacts. Because every time you take a scan, you're only getting a quadrant. So a lot of times what they have to do is, it's like if we want to know this region, you have to overscan. So you get extra information basically around, because we just want, say this is from, let's just for the sake of example, this is from 5 gigahertz to 10 gigahertz. You'll want to increase your frequency scanning essentially to get greater than that. You basically you zero pad your image before you do the processing, because when you're actually going to start doing manipulation, these edge effects are going to cause all kinds of weird issues. So you basically want to oversample. You get aliasing. That's what you're actually trying to prevent. You're trying to prevent aliasing of your image. And what happens is when you scan it, this is from the front view of what you would get, but you get a 2D image because you're taking a camera or a radome, which is like a horn, and it projects. You get a linear transformation that projects as you go with depth, right? And you get it's like a fisheye lens. When you get that image back, all your image is going to come back in a 2D surface. So a lot of your data comes back like this. And in particular, say you had a single point in free space, or points. When you get this data and you start doing Fourier transformations to it, if you don't know that your object, if you don't know that your radar is curved, kind of like a fisheye lens, you'll get weird artifacts where you'll get things bending. Things will start bending. Whereas if you're actually taking reflection data, you have to basically window your function. So you do a linear transformation to kind of bend your mapping, which is what we went over in the first couple lectures. You got to apply filters so that your image isn't a square. You put a window like this, and it causes the natural everything to curve back to how it was really received. So that corrects your reflection to, instead of curving, it does curve originally, but since you've applied this window, it'll correct your RCS data, and so now you're actually getting what you'd get back, essentially. You get what reflection's coming back, because if you don't do windows like this, you're going to get weird artifacts where it curves out. And there's that's a lot of things like this you have to know. It's pretty crazy. If you're really interested, this book is the book on image using RCS imaging and how to receive data with radar in particular. And this particular really goes to larger ranges, so what they use in the military in particular. But and then what you do is you take samples. So your SAR your ISAR will take samples at all these different points, and once you've oversampled and you put it all together, that's when you start getting a diagram. So in particular, you're going to get, with walls like this, you're going to get artifacts out in this range and in this, or in the inverse, sorry. You get backscatter, and then you get a single line like this. So you get kind of a pointed triangle, and then if you had enemy radar or whatever, you would have beaming fields. You just keep this zone from hitting these, and you can kind of navigate around targets. And that's kind of how RCS is used. But there's a large amount of signal processing and image processing that has to go in before you can even get useful data out. It's a lot more complicated than just taking a picture and uploading it on your computer and saying, yep, that's our signature. It's pretty complex, but it's really cool and really fun, and I enjoy it. And this is what I do for my job a lot of times. that's pretty much it.
Again, no questions? Any questions? I guess I should have some questions, right? So how long have you been working on this?
So I used to be a software, so I used to do software on the plane. I work on the B2, and that's what I used to do software on it, and then once I graduated, I shifted over, because I've been working for this company now for almost 5 years.
Yeah.
And now I'm doing survivability, which is we have to basically assess how our plane reacts with radar and if it can survive in a hostile environment. And I've been doing that now for over a year, that particular subset. And that's just doing a lot of planning, working with the military to help determine if the plane has issues, because a lot of times you'll have weird things where your signature is just terrible and it wouldn't be able to fly. So you have to work with them directly. So you have to go out to the airfield. Like I have coworkers right now who are out in Missouri. That's where the station is, and it was like negative 2 degrees for the majority of the week, and they're out on the planes having to look at tape and all kinds of other materials to help determine what's wrong with it. It's a lot of fun. It's just a huge complex system. Every day it's something kind of new. You have an issue and you have to figure out how we're going to read it. Because traditionally, like smaller fighter jets, you can they just stick them on a pylon and they rotate them and you scan it. Super easy. You can't do that with the B2. There's only 20 of them and they cost over $1 billion a piece. So sticking them on a pylon isn't going to happen. And then they also don't want to build models for you because it's really hard to do. And when you're at that scale, you have so much near field effect. So you have to do a lot of things kind of compartmentalized. It's like, oh, we're having a problem on this wing, so we're going to try and like localize the issue there. But you can't get nice full signatures unless you just fly a plane and then have some radar actually scan it, and that costs millions of dollars for just one flight. So you get that maybe every couple months, very, very rarely. So you have to figure out a lot of techniques to figure out problems, and hopefully when it goes to actually fly, you have no issues and the government doesn't get mad at you for wasting money. So.
Did you open over it?
Mm-hmm. Yeah.
So how many times you are on the B2 thing?
How many times of what?
Yeah, you are. So you need to get down to that B2, right? So how many times you need to actually
get in it?
Yeah, get in it.
So I've been in it. I used to work out in California for a little while, and we used to. That's where they do a lot of the take apart the plane. Yeah. Because they have to every year they're taking 2 of them and they have to redo all the parts and clean it and rebuild it because planes are constantly falling apart. Just built in the 80s or 90s, right? And I got to go in and you could climb in it whenever we wanted to and look around and climb in the bomb bay, get in the cockpit. And it's super tight. They have minimized, the pilots are not in comfortable positions, I will say. It is a very tight plane. Fun fact, pilots have to be a minimum height. I think it's like 5'9", 5'8". If you ever see pilots, they're usually smaller. You can't have super tall pilots. It doesn't, they just don't fit in.
So they have a limit of
yeah, like an ideal pilot, you have to have perfect vision. Yeah. And then there's you can't be too tall, because if you're too tall,
you cannot be too short. Like you have
I don't know if it's too short. I think it's more of how tall you are. I mean, at some point you have to be able to reach. But most everything is just instrumentation and fitting in the chair, because the chairs, it's uncomfortable, and they sit in that thing for 36 hours on missions, and they don't leave. I mean, it's horribly uncomfortable. So you don't want to be. If you already have a tough time sitting in a regular airplane and your legs are touching the back seat, you don't want that for 36 hours.
He has to be on diaper for
They have bathrooms.
Okay.
Yep.
But how can you?
It's very uncomfortable. It's very carefully. It's very tight. So it's very you're spaced like this, and you have to squeeze out and then there's a tiny space in the back with a little bathroom area, essentially. It is not comfortable. It is not comfortable at all.
So you need security clearance every time you get into there, or how does that work?
Yeah. To even get close to the plane, you have to be a citizen I think, and it's like 200 feet minimum if you're a civilian, a U.S. civilian. I think it's over 1,000 if you're not a U.S. civilian, and then to actually get on it, you have to be cleared you have to have at least secret.
What's 200 feet? What's that?
200. How many yards is that? It's into meters. It's like a plus.
Oh, you mean 200 feet?
Yeah, 200 feet to it.
You
Yeah.
need
Yeah.
some kind of like different kind of. Oh.
Because they'll have air shows with it, but you can only get within so many feet of the plane. They won't let you any closer. Oh, put you back this laptop.
Yeah, interesting experience.
Yeah, super cool. It's a really cool job.
You graduated here, right? Like
Yeah.
school year, right?
Yeah, I have my I got my undergrad degree from here, and then I work full time, and then I go here too. So it's
So
incredibly busy.
for Vader group here is pretty strong, right? It's actually very strong. So there must be like quite a few good courses. Like which course you recommend like along this line, like for the SARS and ISARS and
Like what is
the courses like that?
why we use this?
No. Not
Oh, the
one.
classes.
Yeah, classes. Yeah.
A lot of there's actually not so any kind of radar class would be good. So I've taken EMF, EMF2. There's a lot of signal processing has been more useful in this because a lot of our radar classes here are more focused in higher range frequencies, where military is kind of lower in comparison because weather, right? Weather's you're using very low to detect water molecules in the air, right? But there is no like formal SAR class. This is just what I have to learn on the job.
Really? Oh, I thought that because I see many of
there might
them,
be
like,
tomography or
yeah.
some kind of cross-section imaging, and I think medical. I think there's one in for
but
because a lot of the
medicals
stuff
are
is
different, right?
medical.
Yeah, it's true, but because so many of like faculty members here seems to working on radar, and so I thought there should be a dedicated class.
So a lot of them do, but they
online.
just don't devote classes to it. Mostly, I think it's because it's so niche. It's such a niche market because a lot of there's so many other applications for radar that it's just they're not using it a whole lot in RCS, and it's and they do use RCS in their other classes, but it's not like for military application. It's not a like using synthetic aperture radar. It's not. As far as I know, I don't know if they have a class on that or not. They might, but I didn't take a class in it. I just had to learn it on my own. So just double E bachelor's and then whatever books they could throw at me, and that's what I've had to learn.
Then the one you recommend is basically a half-track class.
Oh yes, yeah. If you want to learn how to do like the math behind, because you have to do a lot of filtering and figuring out what filters work the best. His DSP class, I think that's the second one. There's the 5,000 level. That class really goes into how to make all different kind of windows, and because that's a lot of it's choosing what window you need, because you can get all kinds of different information depending on how you're filtering out the data, and that class is super useful. And then that's in a one-dimensional case, right? You're just dealing with kind of noise, but to do an image processing, you would take DIP, and that kind of shows you how to take all those lessons you learned in DSP and apply it to a two-dimensional class. A lot of the math you went over at the beginning is pretty much what you go over in Hubble. You do that in way more depth. He'll go over it's like a math class. Highly recommend taking complex analysis. They have it here. If you want to really understand how that math works and how you can take mappings, take that class, and then with a linear algebra class, and then that class, you can really get a great understanding of how this all works. I mean, taking a math class really made things more clear, because that class is very engineering focused, so you're not learning, you do a lot of stuff and you're like, why are we doing it this way? And then the math class kind of resolves, oh, you have to do complex numbers get weird when you start doing like things like Fourier transformations or different mappings. Learning how to map is really important.
Any other questions? If no, thanks our speaker again, and I guess that's the end for today, and see you guys.